Hello students, let us proceed with part 4 of chapter 15, Waves. Now today we are going to study about the principle of superposition of waves. Now we have here in the diagram two pulses with equal and opposite displacement moving in opposite directions. We have a crest and a trough as the two pulses. They move towards each other in the first diagram, and that is they move in opposite directions. Let us see what happens after each second. Now, when the time t equal to 0, we can see the pulses at a certain distance from each other. On the left, we see the crest, and on the right we see the trough, and they move towards each other. After a time t equal to 1 second, you can see that the two pulses have come closer. Now t equal to 2 seconds, the crest is over the trough and they cancel each other. And at the time t equal to 3 seconds, you can see the crest has moved towards the right and the trough has moved towards the left. And in the final t equal to 4 seconds, you can see the pulse directions are completely reversed. So when the pulses overlap, the resultant displacement is the algebraic sum of the displacement due to each pulse. This is known as the principle of superposition of waves. The net displacement is an algebraic sum of the two displacements. To explain it further, let us explain it mathematically. So let y1 xt be the expression for the displacement expression for the first wave, and y2 xt be the displacement expression for the second wave. So when they overlap, then the resultant displacement or the net displacement yxt is given by yxt equal to y1 xt plus y2 xt. Now if we have more than two waves moving in the medium, then the resultant waveform is the sum of the wave functions of individual waves. That is y1 equal to f1 x minus vt, y2 equal to f2 x minus vt, and so on. The nth wave yn equal to fn x minus vt. Then the wave function describing the disturbance in the medium is given by y equal to f1 x minus vt plus f2 x minus vt plus up to fn x minus vt, which can be summarized and written as sigma I equal to 1 to n fi x minus vt. Now this is an expression for the principle of superposition of waves, and it is basic to the phenomenon of interference. Let us watch a video depicting the principle of superposition, and the video courtesy is 7 Active Studio.
The principle of superposition of waves. According to the principle, overlapping waves add algebraically to produce a resultant wave or net wave. In other words, when any number of waves met simultaneously at a point in a medium, the net displacement at a given time is the algebraic sum of the displacements due to each wave at that time. For example, let us consider two waves traveling together along the same stretched string in opposite directions. They met and passed through each other and move on independently as shown in figure. Each picture depicts the resultant waveform in the stream at a given instant of time. The principle of superposition of waves imply that the overlapping waves do not in any way alter the travel of each other. In mathematical form, suppose y1 of xt and y2 of xt are the displacements that any element of the string would undergo if each wave traveled along. When the two waves overlap, the displacement y of xt of one element of the string would be given by yxt equals to y1 of xt plus y2 of xt. In general, it is the wave functions of the moving waves. 1. y1 equals to f1 into x minus vt. y2 equals to f2 into x minus vt, and so on. yn equals to fn into x minus vt. Then the wave function describing the resultant disturbance in the medium is y equals to y1 plus y2 plus so on plus yn equals to f1 into x minus vt plus f2 into x minus vt plus so on plus fn into x minus vt equals to sigma I equals to 1 to n of fi into x minus vt. To illustrate the principle, let us consider two waves of same angular frequency. W equals to of 2 pi by t. Same angular wave number. K equals to 2 pi by lambda. Same amplitude. Are traveling with the same speed along the positive direction of x-axis. If the two waves, one out of phase by a constant angle q, their equations can be written as y1 of xt equals to r sine of omega t minus kx. y2 of xt equals to r sine of omega t minus kx plus phi.
So I hope you watched the movement of the two waves and the superposition of the waves and the resultant wave. Now let us proceed to the mathematical expression for the two harmonic waves which are traveling on a stretched string. Now, as suggested earlier, these two waves will have the same angular frequency omega, same wave number k, same wavelength lambda, same wave speed v, same amplitude a, and both will be traveling in the same positive direction of x-axis. But the two waves differ by an initial phase angle phi. So the two waves can be expressed as y1 xt equal to a sine kx minus omega t and y2 xt equal to a sine kx minus omega t plus phi. As you can see, phi is the phase difference between y1 and y2. Now the net displacement by the principle of superposition is given by yxt equal to y1 xt plus y2 xt. So if you substitute the above equations, you get yxt equal to a sine kx minus omega t plus a sine kx minus omega t plus phi. Now this can be simplified using the trigonometric identity sin a plus sin b equal to 2 sin a plus b by 2 cos a minus b by 2. So here a will be kx minus omega t, and b will be kx minus omega t plus phi. So when you simplify, you get yxt equal to 2a cos phi by 2 sine kx minus omega 2 plus phi by 2. Now if you rearrange, you can get yxt equal to 2a cos phi by 2, and the sine function is kx minus omega t plus phi by 2. So this is the resultant wave which differs in phase by phi by 2 and has an amplitude a phi equal to 2a cos phi by 2. So the resultant wave has an amplitude which varies with phi, or which is a function of phi. Now according to that, we have two special cases here which depend on the value of phi. So the first case is constructive interference, where phi equal to 0. So yxt becomes equal to 2a sine kx minus omega t, or the amplitude capital A becomes a equal to 2 times small a, where small a is the individual amplitudes of each wave. If you look at the first graph, you can see there are two representations of two waves, and the two waves are in phase, or phi equal to 0. They start and stop at the same time. They move together. In that case, the superposition, according to the principle of superposition, the resultant wave will be as shown on the right side. The amplitude of the resultant wave will be, when crest comes over crest, the amplitude will be plus 2a, and when trough comes over trough, the amplitude, negative amplitude, will be minus 2a. So this is the maximum possible value for capital A. And this type of interference is called constructive interference, where the amplitudes add up in the resultant wave. Now the second case is destructive interference. As you see on the left side graph, the crest comes over the trough of each wave. The two waves are not in phase. They are out of phase by an angle pi, or 180 degrees. So the crest does not come over, the crest of one does not come over the crest of the other. The crest comes over the trough and they cancel each other. So yxt will be equal to 0 as shown on the right side. It is just a straight line. There is no wave representation there. So amplitude is 0, capital A is 0, yxt also is equal to 0. The wave has been destroyed. So this case is called destructive interference. Next, let us proceed to learn about the reflection of waves. So here we see a pulse traveling along a stretched string and reflected by a rigid boundary. So it suffers a phase change of pi, or 180 degree, on reflection. This is because the boundary is rigid and the disturbance must have zero displacement at all times at the boundary. By the principle of superposition, this is possible only if the reflected and incident waves differ by a phase of pi, so that the resultant displacement is 0. As the pulse arrives at the wall, it exerts a force on the wall, and by Newton's third law, the wall exerts an equal and opposite force on the string, generating a reflected pulse that differ in phase by pi. You can see the crest touches the rigid wall and returns as a trough. So it has undergone a 180 degree phase difference. Now reflection can take place at a rigid boundary and also at an open boundary. So let us study about the rigid boundary. So just now, as we mentioned, a traveling wave suffers a phase change of pi on reflection at a rigid boundary. So let the incident traveling wave be y2 xt equal to a sine kx minus omega t. Let that be the incident wave. So when reflection takes place, the reflected wave yr xt becomes a sine kx minus omega t plus pi, because it has undergone a phase change of pi. And this is equal to minus a sine kx minus omega t according to the identity sine theta plus 180 equal to minus sine theta, as you know. So according to that trigonometric identity, we get yr xt equal to minus a sine x kx minus omega t. So if you add the reflected wave and the incident wave, your total will be 0. So for a rigid boundary, the resultant wave y equal to y2 plus yr will be equal to 0 at all times. Next is reflection at an open boundary. Now, a traveling wave will not suffer any phase change on reflection from an open boundary because there is no wall or any rigid boundary to reflect it back. That means phi equal to 0. So at an open boundary, the reflected wave is given by yr xt equal to a sine kx minus omega t plus 0, which is equal to a sine kx minus omega t, which is the same as the displacement of the incident traveling wave. Okay students, we will continue later in the next part. This is end of part 4, chapter 15. Thank you.